This is the fourth video in our 10-part series on quantum computing. I'm Professor Priya, and today we'll explore quantum gates and circuits, the building blocks of quantum computation.
Professor, before we start, can you remind us what we covered in the previous videos?
Great question, Sneha. We discussed qubits as quantum bits that can exist in superposition, measurement that collapses quantum states, and the Bloch sphere for visualization. Now, quantum computation proceeds by applying quantum gates. These are unitary operations that transform qubit states while preserving quantum information.
Professor, are quantum gates like classical logic gates such as and OR gates? How are they different?
Great analogy, Arjun. Let's start with single-qubit gates. The Pauli X gate flips states. It turns 0 into 1 and 1 into 0. It's like a quantum NOT gate. The Pauli Z gate introduces a phase. It leaves 0 unchanged but adds a minus sign to 1. This phase difference is crucial in quantum algorithms.
Professor, I understand that the Pauli Z gate changes the phase of 1, but since measurements only give us 0 or 1, why does this phase really matter?
The Hadamard gate is fundamental. It creates superpositions. When applied to 0, it produces an equal superposition of 0 and 1 states. Phase gates like S and T rotate the phase of the 1-1 component. The S gate adds pi by 2 phase, while T gate adds pi by 4 phase. These create precise rotations on the Bloch sphere.
This is fascinating. But what happens when we have multiple qubits? How do gates work on pairs of qubits?
Excellent question. The CNOT gate is a 2-qubit gate. It flips the second qubit only if the first qubit is in state 1. This gate can create entanglement between qubits. The Toffoli gate uses 3 qubits. It flips the third qubit only when both control qubits are 1. It's universal for classical reversible logic computations.
Professor, how do we combine all these gates together? Can we chain them to create more complex operations?
Absolutely, Sneha. A quantum circuit is a sequence of gates applied to qubits. We read circuits from left to right like a timeline of operations. Here's a famous example. Applying a Hadamard gate followed by a CNOT creates an entangled Bell state, a superposition of 0, 0, and 1, 1.
Wow! So the qubits become connected through entanglement. If we measure one, it immediately affects the other, right?
Exactly right. Let me summarize. Gates are unitary operators acting on qubits. Single-qubit gates rotate states on the Bloch sphere. Multi-qubit gates enable entanglement between qubits, and quantum circuits combine these gates into complete quantum computations. In our next video, we'll focus on entanglement and quantum phenomena, including quantum teleportation and Bell's theorem. Thank you for joining us.